All right, so picking up where we left off on 53. Now, for this one, we have a point outside of our circle, and it tells us that we have these two tangents. Well, anytime we have two tangents drawn from an exterior point, you should know that those two lines are going to be the exact same measure. So on here, they want to know which one of these statements must be true. Well, I don't even know what they're trying to say for A. I think they left something off because it just says segment TR. Doesn't really tell us anything. On B, angle S is always smaller than T and R. That's not true. As you got closer and closer to that circle, that would not be true. C, triangle STR is always an isosceles triangle. Well, since S has to be the same distance from T and R all the time, C would be true. And then for part D, it can never be a right triangle. No, that's not true. As you got closer, there would be a point where S would become a right angle. So D is not true either. So C is the only one that's correct. On 54, this one, again, we have our two tangents. This time we're talking about angles. The only thing that they tell us is that this, where was it? Angle ZWX, this one is 70. Now, this angle intercepts this arc, right? So this arc is double that inscribed angle, which would be 140. Then we also know that the arc across from it, and this entire arc all the way around, is the other half of the circle. A circle is a total of 360. So if we subtracted the 140 from 360, we'd be left with 220. And then we want to solve for y over here. So I'm just going to call this y. That's the measure that we're looking for. So y is going to be equal to the big arc minus the little arc divided by 2. That was our equation. Anytime we had an angle on the outside of the circle, it was big arc minus little arc divided by 2. If it was inside the circle, then it was the two arcs added together divided by 2. So on here we got 80 divided by 2, which is 40. So that's C. All right, next on 55. All right, here we have two angles that are intercepting the same arc. Up here at the top, there's GJ. This arc is being intercepted by both angle H and angle K. So what should be true about those two angles? They should be the same. So these two angles must be congruent since they're intercepting the same arc. Because let's say, for example, that this arc was 70. Well, then this angle would be half that arc. This angle would be half that arc. It has to be the same measure. They couldn't be two separate measures. So it's not possible for one to be 35 and one to be 30. Which one's telling us that? That's option C. On 56, we have chords that are drawn into this circle. And when we have those chords, since they're intersecting, the two parts of the one chord multiplied together should be equal to the two parts of the other chord multiplied together. So writing this as an equation, we have 2 times 3x minus 2 equals x times 5. Multiply it out. So we're distributing that 2. 6x minus 4 equals 5x. Bring the x's to the same side. So I'm going to go ahead and subtract 6x from both sides. When we do that, we end up with negative 1x. We can't have a negative there. We need to divide off the negative 1. So that just gives us x is positive 4. That's not what we were trying to find, though. They want us to find kz. So kz was those two parts together, 2 plus 3x, which we now know is 4, minus 2. So 2 plus 12 minus 2 is 12, which is answer choice D. All right, on 57, quadra ABCD is inscribed in a circle. What you should remember about inscribed quadrilaterals is that the opposite angles are supplementary. So they want to know angle B up here at the top. Well, B and D are opposite angles. Those two have to be supplementary with each other. So 180 minus 80 is 100. On 58, quadrilateral ABCD is inscribed into a circle. So we need to draw this. They also told us that AB and BC are not the same length and that segment AC is the diameter. So I'm going to first draw my diameter. But then I need to draw on this quadrilateral as well. So I'm going to put a B over here and a D somewhere over here. And the only thing that we know for sure about this figure is which one of those four things. Which one do you think is true? Now that you have the diagram, maybe it'll help. It's not a rectangle. Nope. C. We have at least two right angles in here. No matter where we put B and D, these two are going to have to be right angles because they are now inscribed into a semicircle. And if it's inscribed into a semicircle, that angle has to be half of its intercepted arc. A semicircle is 180 degrees. So 180 divided by 2 is 90, no matter what. So anywhere we put B or D, they had to be right angles. Now, could A or C also be right angles? Possibly. But it doesn't have to be a rectangle. It doesn't have to be a trapezoid. It doesn't have to be anything else. Well, all we know is those two angles must be 90. All right, 59. This is kind of the same idea as that first question that we did today. We have all these tangents. So up at the top, both of those pieces are congruent. To the right, both of these are congruent. To the left, both of these are congruent. They give us lengths for each part. So they give us AF, which is 6. So AD also has to be 6. CD, it says is 5. So CE would also be 5. BE is 4. So BF would also be 4. Now they want to know the perimeter. So now that I have all the numbers in there, we can just add them all up. Or if you wanted to go back to the original values, if you added the originals, we ended up doubling each one of those. So those three numbers add together is 15 times 2 is 30. Either way, you should get a total of 30 for the perimeter. Which statement is valid when a circumscribed circle of an obtuse triangle is constructed? So there is one answer here that should stand out. If we have a circumscribed circle, no matter if it's obtuse or not, the only answer on here applies to any circumscribed circle. So I'm going to draw an obtuse triangle real quick. And if we were finding a circumscribed circle, it'd be by drawing in our perpendicular bisectors. So I'm just making a sketch of them. I don't actually know where they are, but it'd be something like that. They meet at a common point. This would be the center of the circle, and the circle would have to, I know that's just a rough sketch and it looks horrible, but that's the idea. So the first thing says the longest side of the triangle lies on the diameter. No, that's not correct because the point is outside of the circle. So that doesn't work. The next one, the circle is drawn inside, touching all three sides. That's not a circumscribed circle, that's an inscribed circle. So that's not right. The center of the circle is on the interior of the triangle. Nope, it's on the outside. And finally, the vertices of the triangle all lie on the circle. Like I said, even though they told me about the obtuse triangle, D is the answer for any time you have a circumscribed circle. A circumscribed circle should always go through the vertices of the figure. All right, then we come to area of a sector. So we have our formula for area of a circle, which is pi r squared. The difference with area of a sector, and some of these formulas are still up there on the board. Area of a sector is going to be our measure over 360 times pi r squared. So we had two formulas that were very similar. Area of a sector and then our arc length. Again, it's the fraction that we're using times, if we're doing a sector, we're doing area, so our area formula. If it was arc length, then it'd be our circumference formula. But again, that's our equation. So plug in, you have 120 over 360 times pi. It says the radius up here is 5 squared. 120 out of 360, that reduces to 1/3. And then we have 5 squared is 25. Multiply that by that fraction. Look at all of our answer choices. They left it as a fraction. So when we multiply to that fraction, that just goes to the top. So it's 25 pi over 3, which is option A. On 62, it tells us that these 3 pieces are all congruent. This is a concentric circle sharing that same center point. So the values on the other side would also be the same. And the whole thing across, all the way from P all the way to K, is 42. If I wanted to split that in half, the diameter of the big circle is 21. What's each of the small pieces? Well, whether I did 21 divided by 3 or 60, or 42 divided by 6, I get the same answer of 7 for each of these little pieces. Now, what's the closest area to the shaded region? We have the big circle that we need to find minus the smallest circle on the inside. But again, it's only half of the circle. So I'm going to write this out as 1/2 pi, and we have a big circle that we're going to use, so pi big R squared, minus 1/2 pi, and we have our little circle, so little r squared, 21. Our small radius is 7. So 21 squared is 441. 7 squared is 47. Whoops. 49, I mean, sorry. So again, 1/2 of each of these, we'd have 220.5 pi minus 28.5 pi. When we subtract those, we'd be left with 192 pi. Now, 192 pi is not an answer up there. We actually have to multiply out pi, which is going to be roughly. Ooh, did I do something wrong? My answer is not up there. I did something wrong. What'd I do? Oh, this is 24. 24. That's my mistake. I put 28. That should have been 24. So it should be in 196 pi. So our final answer is 6157, which rounds up to D, 616. All right, on 63. All right, this time we have a bicycle spoke. So now we're dealing with arc length. Arc length equals m over 360 times. You could either do pi times diameter or 2 pi r, doesn't matter. You're using the circumference. On this one, they gave us a diameter, so we might as well use the diameter. They also told us that we have this separated into 10 equal parts. So really, instead of finding the angle measure, since I'm just doing one of these, 10, I'm doing 1 out of 10, so that's 1/10. I could just replace that fraction with 1/10. What? We have 18 for our diameter. Multiply that together. 18 over 10 pi. That's going to be 1.8 pi. All of our answers are in decimals. We need to multiply it out, which is going to give us roughly 5.7 if we round. All right. Now, there is one thing that I did not do when it came to circles. I did not have us do anything with radians. If they ask something with radians on the exam, it is something that's pretty easy to convert. So I'd rather you just do everything in degrees and then convert in the end if necessary. All right. So the idea behind radians is in a circle, if we started from 0, went to half a circle, that's 180. Came all the way around, that's 360. Radians is a way to measure angles based on the length of its arc. So on here, we start off 0 is the same as 0 pi. 180 is the same as 1 pi, or just pi. 360 is the same as 2 pi. All right. So the way you convert from degrees to radians, so if you're going degrees to radians, you're going to multiply by pi over 180 because they are equivalent. They're the same angle measure. If you're going the opposite way, radians to degrees, you just multiply by 180 over pi. So it's those same two values. It's just whatever you're changing it to goes on top, just like any other conversion. You're to convert inches to feet, then we multiply by 1 over 12. All right, if you did the other way, converted to inches, then you do 12 over 1. That's what you multiply by. So again, whatever you're changing it to goes on top. All right. So first thing, we're not changing the way that we do this problem. We're still doing it the exact same way that we've done before. It's just at the very end, we're changing our answer to radians. So on here, we have an arc length given to us of 2 pi. So we have arc length equals m over 360 times pi. Actually, let's do instead of pi d, we'll do 2 pi r. So times 2 pi r. We can plug in the values that they gave us. So arc length is 2 pi. We have m over 360 times 2 pi. The radius on this one was 10. Now, first thing we can do, both sides have 2 pi right now. So I could divide off 2 pi so that this side now is just 1. And on this side, it's going to end up going away. So we now have 1 equals m over 360 times 10. Get rid of the 10 by dividing it off. So 1/10 equals m over 360. Multiply 360 to the other side. That's 360 over 10 equals m, which is 36 equals m. That answer's in degrees, though. None of our answer choices are in degrees. So that's where we have to now convert. So we have 36 times, we're going 2 radians, so pi is on top, 180. So 36 times pi over 180. 36 goes into itself once and goes into 180 5 times. So that's pi over 5. That's in radians. So that's our extra step there, converting to radians. Radians become much more important when you get into like trig. I don't even think they're going to do radians in algebra 2 next year. I think it's not in the curriculum anymore starting next year. So you probably won't have to worry about that until trig. All right. On 65. All right. There is a error in our answer choices there. It says n. Those should be pi's. So this should be pi, 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 pi. So I got kind of screwed up. But they gave us a circle separated into 30 sectors. And then they said they took 2 sectors and combined them. So now it looks like almost a rectangle here. And they said that the radius is one of the sides. The other side is the length of one of those arc lengths of a sector. So we need to figure out what is that arc length. So the arc length for this one, we already know it's 1 out of 30. And we're doing pi, 2 pi r. So we get 2 out of 30, which is 1/15. Now, notice how all these are in. They've actually multiplied it out. So pi and r multiplied to the top there. So this is our other side. And again, for area of a rectangle, we're just multiplying base times height. So we have r times pi r over 15. Which on here, if you look at all of our answer choices, It was A. Bingo. I can't see my pen out here. There it is. Sorry, my pen had disappeared. All right, let's try that again. So final answer, again, was the same as A. On 66. Now, I don't really like the way they did this question, but they took the prism, they separated into 3 separate pyramids so they're all equal. They wanted to know what's the volume of each pyramid. Well, we have a formula for area volume of a pyramid, and that's 1/3 base area times height. That's none of the answer choices that are here. Now, in order to do this, the tricky part is they're actually going back to our perimeter over here. So although they talked all about these pyramids, they are looking at the prism that's on the left. So the area of the base of the prism is A. The height of the prism is T. So all we actually have to do is replace big B with the capital A and height with T. And then we have our answer, which is D. So that's it. On the next one, 2 cylinders, a sphere, and a cone are shown. Select the 2 objects with the same volume. So first, writing out the formula for each one. Volume of the first one we found by doing base area times height. So pi, the radius on this is 1.5, height of 4. On the next one, volume equals, it's a cone, so 1/3. Base area, again, pi r squared, times the height of 2. Then we have our sphere. The formula there is 4/3 pi r cubed, so this is 2. And finally, the last one with the radius of 1 is going to be volume equal times the height of 6. All right, going through these, which 2, just from looking at the formulas, do you think are going to be the same? Any guesses? So the cone and the sphere both have that fraction in there where we have dividing by 3. We have some similar numbers. We have 4s and 2s. So I would say that's probably those 2. So we're going to check those 2 first. So on the sphere, if I simplify this, 2 to the 3rd power is 8. 8 times 4 is 32. On this one, 4 squared is 16. 16 times 2 is also 32. So 32 thirds pi. So both of those are the same, this sphere. All right, on 68, this one, I think there are actually 2 answers on here. Because when we talk about Cavalier's principle, yes, if you're dealing with a prism or a cylinder, you could talk about the area of the base and the height having to be the same. That would work for any prism or cylinder. But that doesn't work for all shapes because a pyramid and a cone come to a point. So for those 2, we really have to talk about the cross section at all the different levels. So the cross section at every level has to have the same area, which they talk about that in options A and C. Now, they do have to have the same height, but if they have the same area at every single cross section at every level, that's kind of taken care of. So I know C says something extra about the height, which is correct, but do you actually need that part? It's already included when you do the cross section at every level. So A or C could be seen as the correct answer here. On 69, all right, you can do this a couple ways. The diameter of a basketball is approximately 9.5 inches, and the diameter of a tennis ball is approximately 2.5 inches. The volume of the basketball is about how many times greater than the volume of the tennis ball? Now, you can do this a couple different ways. You could plug this into our volume formula, which is the 4/3 pi r cubed, and you could do both volumes and then compare the 2 volumes. But there is a shorter way. We're looking for how many times greater the volumes are. So essentially, we're looking for the volume ratio. So we already have the basketball is 9.5. The tennis ball is 2.5. This will give us our scale factor. Our volume ratio will then be our scale factor cubed. Again, you could cube each one individually and then divide them, or divide them and then cube them. It doesn't matter. So I'm dividing first just to keep our numbers small. 9.5 divided by 2.5 is 3.8. And that cubed is roughly 54.872, which is C. On 70, the ratio of the volume of two spheres is 8, my bad, 8 to 27 is our volume ratio. What is the ratio of the lengths of the radii of the two spheres? So we're going backwards. We need our scale factor. What do we need to do to these in order to get our scale factor? We have to, these were originally cubed, right? So we have to uncube it. So just like the opposite of a square root, opposite of squaring something in square root, we have to take our cube root. So I would just do that on a calculator. That'd be 2 and 3, right? Or just ask yourself, what times itself 3 times gives you 8? What times itself 3 times gives you 27? So that's 2 and 3. So what is the ratio of the length of the radii of the two spheres? That's going to be 2 to 3. Or if you want to write it sideways like they did with the colon, that's fine too. All right, on 71, a cup of water in the shape of a cone has a height of 4 inches, a maximum diameter of 3 inches. What is the volume of the water in the cup to the nearest 1/10 of a cubic inch when the cup is filled to half its height? All right, so you have a cone cup, looks something like this. They said that the cone has a maximum diameter all the way across right here of 4. And then they said that the height of the cup is, whoops, sorry. The diameter is 3. The height is 4. Let me make that look better. All right, so again, height is 4, diameter is 3. What is the volume of water in the cup to the nearest 1/10? So they did say that it is filled only half the height. So we don't need to use the whole height. We're only going to here. That's how much water is in here. So the height here is actually only 2. As for our diameter, what's our diameter now at half the height? It's also going to be half. So 1.5. So for our formula, we're going to do volume equals 1/3 pi r. What's our radius if our diameter is 1.5? 0.75, right? That's half. And then times our height of 2. So 1/3 pi multiply by 2, divide by 3. We get 0.375 pi times pi. That's 1.178, which is close enough to E. All right, on 72. Wait, how many minutes do we have left in here? Yeah, we can still do a couple more. All right, 72. The planets in our solar system can be modeled using spheres. The diameters for Jupiter and Saturn are shown in the diagram below. The volume of Saturn is 59.9% the volume of Jupiter. What is Saturn's diameter, D, in kilometers? All right, right answer to the nearest 1,000. All right, so on here they told us that the volume was 59.9% the volume of Jupiter. So we have basically, we could call that a volume ratio of 0.599. We want to go backwards to scale factor. We have to uncube it. So take the cube root of 0.599. What was it? 0.599. So that gives it a scale factor of 0.842. So they already gave us the diameter of this one. So all we need to do is multiply by that scale factor. So times 0.8429 gives us sorry, that was a comma, not a 2, 9. Now they said to the thousandths place. So we need to go to 3 decimal places. That'd be our answer. All right. On 73. Which of the following is the best description of the resulting 3-dimensional figure if a right triangle is rotated about a line containing its hypotenuse? So if we had a right triangle and it was rotated about this line, yeah, these aren't moving. This is going around. So it looks like 2 cones that are sharing a base. So that'd be option C. All right, last one. William is drawing a picture of cross sections of a right circular cone below, which drawing cannot be a cross section of the cone. Triangles right down the middle. This half of an ellipse, that's possible if we go vertical on one of the sides. D, if we go diagonally do that, we could get D. The only one that doesn't work is A, because there are no straight lines like that. And that would give us a square. All right, we're going to stop there. So we got to 74. We'll pick up on 75 tomorrow. Like I said, if you already got this assignment done that was supposed to be due today, great. That's all you need. The other one, I'm not going to actually start going over until Tuesday. So make sure you finish it out. If you didn't finish the one that was supposed to be due today, make sure you at least get that one done for tomorrow so you still get full credit for it. Like I said, I'll push the dates back for those 2.